Okay. So the question is from the review sheet, chapter 17, problem number 29, which was to calculate a certain line integral using Green's theorem. So the line integral, it's xy squared dx plus xy squared dy. And the curve C is a triangle. Oops, with vertices. Let me just make sure I'm okay. Yeah, I am recording. It's a triangle with vertices 0, 0, 2, 0, and 0, 2 going in a counterclockwise direction. So in the XY plane, this is 0, 0, this is 2, 0, this is 0, 2. So we're going counterclockwise around this triangle like this. And we want to compute this line integral and using either form of Green's theorem. So for that, it is certainly useful to write down Green's theorem and figure out what the application would be. So in Green's theorem, this relates the integral around a curve to an integral over the region inside the curve. And Green's theorem says that, so this is Green's theorem. The integral around a closed curve of some vector valued function f dot dr, which is can be written exactly in this form, some function f dx plus g dy, where f, this is a vector field. So this is a vector with two coordinates, two components, and the first coordinate is little f of xy, and the second coordinate is little g of xy. So that's the relationship between the vector field f and the scalar functions f and g. And Green's theorem says this is equal to the double integral around R of the partial of g with respect to x minus the partial of f with respect to y, that scalar function integrated over the region. So what is my vector field? My vector field is f of xy equal, so the first component is xy squared, and the second component, sorry, I wrote this down wrong probably. Let me just go find this problem again. It's always helpful to write the problem down correctly. So problem number 29 is xy squared, and g is x squared y. So xy squared, x squared y. So my function little f of xy is the scalar function xy squared. G of xy is the scalar function x squared y. The partial of g with respect to x is y squared. The partial of f with respect to y is x squared. So for example, if I wanted to look at this integral, this is the integral over R of the function partial g with respect to x, x squared minus y squared dA. So this is a scalar function, and let's see how we might integrate that. So we're looking at, this is my region R, this triangle. This, you might say, this is y equals 1 minus x. So this is a double integral x goes from 0 to 1. And for each x, y goes from 0 to 1 minus x squared minus y squared. So our problem is to compute this integral. So the double integral over R of partial g with respect to x minus partial of f with respect to y dA. This is a double integral of x squared minus y squared dy dx. Y goes from 0 to 1 minus x, and x goes from 0 to 1. And you unpeel this onion from the inside out. What is this integral? The integral from 0 to 1 minus x of x squared minus y squared dy. When you integrate x squared with respect to y, x squared is like a constant. The integral of 1 dy is just y. When you integrate y squared with respect to y, you get 1/3 y cubed. So we're integrating this from y equals 0 to y equals 1 minus x. So we get,
please. Thank you.
when y is 1 minus x, this is x squared times 1 minus x minus 1/3 1 minus x cubed. And when y is 0, this is 0. So this expression is what's inside this integral. So this becomes the integral from 0 to 1 of x squared minus x cubed minus 1/3 1 minus x cubed. I can write that if I like as plus 1/3 x minus 1 cubed dx. And what is this integral? Well, the integral of x squared is 1/3 x cubed. The integral of x to the 3rd is 1/4 x to the 4th. The integral of x minus 1 cubed is 1/4 x minus 1 to the 4th. So I'm evaluating this from 0 to 1. When x is 1, I get 1/3 minus 1/4 plus 0. When x is 0, I get 0, 0 minus 1/12. So 1/3 minus 1/4 is 1/12. So if you put this over, this is like 4 over 12 minus 3 over 12 minus 1 over 12. We get 0.
Professor, where do you get 12?
What?
Where do you get 12? Minus 12, well, 1 over 2. Well,
3 times 4 is 12.
Oh, that one is 3? Okay.
Yeah.
Okay,
This is
thanks.
a-
Thank you.
Now, so we got 0. Now, that's interesting because let's go back and look at the original problem. So the original problem was to integrate around this triangle xy squared dx plus x squared y dy, these parentheses, which is the integral around of a certain vector field. And what is the vector field? The vector field had components xy squared, x squared y. And so this is the little f and this is the little g. Now, if I take the partial of f with respect to y, I get, that's the partial with respect to y of xy squared. That's 2xy. if I take the partial of g with respect to x, that's the partial derivative with respect to x of x squared y, that's also 2xy. So the partial of f with respect to y equals the partial of g with respect to x, which means f is a conservative vector field. F is the gradient of some vector field phi. And in fact, if we want to find phi, the partial of phi with respect to x is going to be xy squared. So phi is the integral of xy squared with respect to x. That's a half x squared y squared. Well, actually, a half x squared y squared will do it. If you take phi to be equal to a half x squared y squared, the partial of phi with respect to x is xy squared. The partial of phi with respect to y is x squared y. So f is the gradient of phi, and another form of Green's theorem says, or it's the fundamental theorem for line integrals. It says if you integrate a line integral of a vector field that's conservative around a closed curve, you always get 0. And that's what happened in this case. So this is a second proof that this integral is equal to 0. We could also have evaluated the line integral directly, but that would have involved 3 integrals, because you would parametrize the horizontal line from 0, 0 to 2, 0 in one way. Then you parametrize the line from 2, 0 to 0, 2, that's a second integral. Then you parametrize the vertical line from 0, 2 to 0, 0, that's a third integral. And you calculate those 3 integrals, and again, you should get 0.
Hmm. Right.
Professor, so the questions on the exam review, like, are those the way that it's gonna be formulated, like on the test, or are they gonna look more like my math labs questions for the questions on the final?
It'll look more like the review questions, because that's what a question normally looks like. Here's the
Okay,
problem, find the answer. Just
okay,
like the midterm. Midterm was the same way.
just like the midterm. So what's it? All the questions on the review are types of questions we're gonna see on tests. Like, are there like any that you gave us like as like a challenge, just like no? Or are all these types of problems gonna be on the final?
Oh, well, there's way too much on the review to be on the final. The final is much, much, much shorter than the review.
Okay, so you gave us like the harder problems, like you said, like last time, like, so like we could do the ones on the final like easy, right?
Well, I don't know. I'm not sure about that yet, because I haven't made up the final, but
Oh,
the review problems certainly cover the material in the course.
okay,
But it's a subset of that that is on the final.
okay, thank you, Professor.
Sure.
Professor, number 30.
Number 30 on the same page?
Yes, sir.
Okay,
Thank you.
let me try and find that. So this is again on chapter 17, page 1183, number 30. And number 30 is, again, a Green's theorem problem. We want to compute the integral of minus 3y plus x to the 3/2
Yeah.
dx plus x minus y to the 2/3
DY.
dy. And C is the boundary of a half disk. So it's the half disk that looks like this
Hmm.
from 2, 0 to 0, 2. So C is the boundary of the half disk that goes counterclockwise. So we're going horizontally along the x-axis and then around the circle like this. And my vector field F with components F and G is given by minus 3y plus x to the 3/2, comma, x minus y to the 2/3. So this is my function little f of xy. This is my function little g of xy. And we can check, let's see, that the partial of f with respect to y is minus 3. The partial of g with respect to x is 1, and they're different. So my vector field F is not a conservative vector field. So we can't just say without any more calculation that the integral is 0. But we do know that this integral, let me just call this I or L, this line integral L, is also equal to the double integral around the region R. The region R is the region inside this semicircle of the partial of G with respect to X. Let me just make sure I write it the same way every time. Partial of G with respect to X minus the partial of F with respect to Y. So that's the double integral over this region. If this is the function G, the partial of G with respect to X, well, that's just 1. And the partial of F with respect to Y is minus 3. So that's the double integral over this region. 1 minus minus 3 is 4 dA. That's just 4 times, when you integrate 1 over a region, you just get the area of the region. What's the area of a circle of radius 2? The area of a circle is pi r squared. If r is 2, r squared is 4. So the area of a circle of radius 2 is 4 pi. This is a semicircle, that's half of it. So this area is 2 pi, so we get 4 times 2 pi, or 8 pi, and that's the answer.
Hmm.
Now, we could see how do we actually, if we want to try to calculate this line integral directly, that is using this expression, how would we do that? So how will we parameterize this curve that goes counterclockwise across the x-axis and then around the top half of the circle? So when you go from minus 2 to 2, you can parameterize that by r of t is equal to, let's say, for example, just t, as t comma 0, as t goes from minus 2 to plus 2, right? As t goes from minus 2 to plus 2, r of t is going from minus 2, 0 to 2, 0. Let me just call this r1 of t. And r2 of t, that's when you're moving around the circle from here around to here. How would you parameterize that? Well, you could say r of t is cosine t, 2 cosine t, 2 sine t, as t goes from 0 to pi. When t is 0, this is 2 comma 0. When t is pi, you're at 0, 2. When t is pi over 2, when t is pi, you're at minus 2, 0. So I want to calculate the integral around this curve of minus 3y plus x to the 3 halves dx plus x minus y to the 2/3 dy. Well, this actually might be rather difficult to do, so we'll just experiment. So if we want to integrate along just the line from minus 2, 0 to 3, 0, so if x of t is equal to t and y of t is equal to 0, right? That's what we have here. So the integral t goes from minus 2 to 2, minus 3y plus x to the 3 halves dx plus x minus y to the 2/3 dy. Well, sorry, the integral along this first part of the curve, C1. That's the integral. T goes from minus 2 to 2, minus 3y, y is 0, x to the 3 halves, that's t to the 3 halves, dx dt is 1 dt, and x minus y to the 2/3 dy, dy dt is 0. It's just t to the 3 halves. This is 2/5 t to the 5 halves, evaluated from minus 2 to 2, whatever that turns out to be, some unpleasant mess, I guess. This is 2/5 Yeah, forget this. I mean, the whole point of Green's theorem is when something is complicated, you can do it one way or the other way. You choose the easier way. And the easier way was to use the integral part of Green's theorem, this part, to calculate the integral. And we got that the answer was 8 pi, and that was pretty good.
Professor.
Yeah,
Yeah, on the part of that question, right? Why do we need what do we do with x squared plus y squared?
x squared plus y squared.
Yeah, it's a part of the question.
So what the question says is C. So this is the statement from the question. C is the boundary
Oh, they apply. Have this.
of the half disk x squared plus y squared less than or equal to 2, y greater than or equal to 0. If you look at the disk x squared plus y squared less than or equal to 2, that's the whole inside of the circle,
Okay.
radius 2.
Mhm.
All right. But if you're only looking at the part with y greater than or equal to 0, that means you're looking at just the top half of the circle of the disk, what I just put in red.
Mhm.
So that's where the x squared plus y squared less than or equal to, I'm sorry, actually I made a mistake. It should be square root of 2. If it's x squared plus y squared less than or equal to 2, this is the circle. It's the disk of radius square root of 2. So the answer is going to be slightly different. So x squared plus y squared less than or equal to 2, that's everything inside the circle of radius square root of 2. That is the disk.
Mhm.
And y greater than or equal to 0 means only look at the top part of the disk.
Okay. Thank you.
If it's square root of 2, this would have been, the area would be 2 pi, half of the area of the upper half of the disk would be pi. So the answer would be 4 pi and not 8 pi.
Number 24.
Sorry,
Number 24.
in the same set?
Yeah. What would you call it?
So
Chapter 17.
this is again, page 1183, number 24. To compute a line integral. So the vector field F is given as the gradient of the scalar field x squared y, and C is the curve parametrized by R of t equal to 9 minus t squared t for t between 0 and 3. So in this parameterization, x is equal to 9 minus t squared and y is equal to t. So so this is a parabola going sideways. This is like saying x is 9 minus y squared. What does the graph of this look like? So the y component goes from 0 to 3. And when t is 0, this is 9. So 0, 3, 3, 6, 9. When t is 0, we get 9, 0. When t is 1, we get 8, 1. When t is 2, we get 5, 2. And when t is 3, we get 0, 3. So we're looking at this parabola, part of a parabola, where when t is 0, you are here, and you're moving along this parabola from the point 90 to the point 03. So that's my curve, right? So it's always good to draw a picture of something when you can. And we want to calculate the integral along this curve of f dot dr. And let's do it the hard way by parametrizing C. Well, here C is parametrized. So this is, what is F? So F is the gradient of x squared y. So this is a vector field. The partial derivative of x squared y with respect to x is 2xy. The partial derivative of x squared y with respect to y is x squared. So F is the vector field 2xy comma x squared. So this is going to be an integral. C is the curve where t goes from 0 to 3. And F dot, so R of t is 9 minus t squared t. R prime of t, when you differentiate, is minus 2t comma 1.
Professor,
Yeah,
on the partial derivative, we have 2s minus sy.
I'm sorry, I didn't understand what you're asking.
On the partial derivative for sy squared is equal to 2s minus sy squared. Is that correct?
So the partial derivative so x squared y, if you differentiate with respect to x, you get 2xy.
Okay, what about
If you differentiate with respect to y, you get x squared. So f is a vector field, and that means f of xy is a vector, and the first coordinate is 2xy, and the second coordinate is x squared. Okay. And we want to compute the line integral. And the line integral is, let me just write down the simplest form of it in the way it's given in the text. So for the line integral of a vector field, this is the integral from 0 to 3 of the dot product of f with the velocity vector r prime of t dt. So f is 2xy x squared. Let me just write this down explicitly. So f is 2xy comma x squared dot product with r prime of t, which is minus 2t comma 1 dt. But of course, x, r of t is 9 minus t squared comma t. So x of t is 9 minus t squared, and y of t is t. So 2xy is 2 9 minus t squared times t, which is 18t minus 2t cubed. And x squared is 9 minus t squared is 9 minus t squared squared is 81 minus 18t squared plus t to the fourth. So when I take the dot product of 2xy with minus 2t and x squared and 1, 2xy times minus 2t, so 2xy times minus 2t is this times minus 2t, is minus 36t plus 4 t to the fourth. Sorry, minus 2t is minus 36 t squared plus 4 t to the fourth plus x squared, that's this, dot product with 1, plus 81 minus 18t squared plus t to the fourth dt. So if I did the arithmetic correctly, which I'm certainly not willing to guarantee, we have the integral around this curve of f dot dr. It's not a line, it's just a line integral, it's not around a closed curve. It's this integral, the integral from 0 to 3. I have 81 minus 54t squared plus 5t to the fourth dt. So this is 81t minus 54 times 1/3 t cubed. 54 over 3 is 18 t cubed plus t to the fifth, evaluated from 0 to 3. So this is equal to 243 minus 18 times 27. Let me just write everything in terms of powers of 3. So 81 is 3 to the 4th times 3, that's 3 to the 5th, minus 2 times 3 squared times, so minus 2 times 3 to the 5th, plus 3 to the 5th, that's 0. So
Hmm.
I got 0 when I calculated this line integral directly. But then the problem also says calculate the line integral using the fundamental theorem for line integrals. The fundamental theorem of line integrals says that if you take an integral around a curve of f dot dr, and if your vector field is the gradient of a scalar field, this is just, and if your curve is from some point A, which in our case is 9, 0, to the point B, which in our case is 0, 3, this is going to be phi of B minus phi of A. Now we're, in this case, for this problem, phi of xy was equal to x squared y. So this is going to be phi of 0, 3 minus phi of 9, 0. Well, this is easy. This is 0 squared times 3 minus 9 squared times 0 is 0 minus 0 is 0. So using the fundamental theorem of line integrals, we get the answer immediately with a lot less work. But fortunately, it's very nice that we got the same answer both ways we did the problem, which gives us some confidence that we did the problem correctly.
Hmm. Thank you.
So Professor, to solve this problem, we could do either or, the top version or the bottom version to
Well,
solve
if,
this.
if this were an exam problem, I would just say, so, compute the integral. In the review problem, it said do it both ways.
Okay, so you
Right.
recommend doing the first way of solving it, just regular computing instead of using the bottom one, bottom
Oh,
method.
bottom one is much better.
The bottom one you would recommend to use?
This, yeah, I got the answer in a second. I didn't have to do any work.
Okay,
For the first one, I did
like
all of
almost
this
like,
calculation. I mean, it was a lot of work.
yeah.
So we were told to do it both ways, but
Mhm.
as a rule, I mean, if you're given a problem to solve, you want to get the right answer. But
Mhm.
the less calculations you do, the less likely it is you're going to make a mistake anyway. You
Okay.
just want to get the right answer.
Right. Thank you, Professor.
Sure.
So I'll try to use the bottom method.
Well, yeah, but the bottom method doesn't always
It doesn't always
necessarily
work. It just depends on
Yeah.
the type problem. Yeah.
But of course, if you know your vector field is a gradient, then the bottom way is by far the best usually,
Okay.
because you just compute the scalar function phi at the endpoints and subtract, and that's the answer to the integral.
Okay. Thank you, Professor.
Sure.
Question number 20.
Number 20 in the same set.
Yes,
Okay,
thank you.
I'll try to do it. Hope it's not too hard.
Let's see.
Okay, let me go back and find the problem. Okay. Review exercises. Number 20. Okay. So again, this is page 1183, number 20. So we have a vector field F equal to y squared 2xy. So if you think of this as a function, a vector function where the first coordinate is little f and the second coordinate is little g, then f of xy is y squared, and g of xy is 2xy. And if I take the partial of f with respect to y, I get 2y. If I take the partial of g with respect to x, I get 2y. So these are equal. So partial f with respect to y equal partial g with respect to x implies f is a conservative vector field. So f is equal to the gradient of some function phi. So phi is some function of two variables, and it has the property that the partial derivative of phi with respect to x is y squared, and the partial of phi with respect to y is 2xy. So I need to integrate to try to find phi. So if the partial derivative of phi with respect to x is y squared, that means phi is the integral of y squared dx, right? Which is going to be y squared x plus maybe some other function. So this has to be something which, when you differentiate with respect to x, gives you y squared. So y squared x plus some other function, maybe I'll call it, I don't know, h of y. Because if you differentiate this with respect to x, you get 0. So phi is y squared x plus h of y. And the partial derivative of phi with respect to y is going to be 2xy plus h prime of y, which means, but this has to be 2xy. So h prime of y is 0. So h of y is just some constant. So I can take any constant. I'll just take the constant to be equal to 0. So phi of xy is equal to xy squared. And then the gradient of phi, differentiate this with respect to x, I get y squared. Differentiate this with respect to y, I get 2xy. And that's the function f that I started with. So f is this vector field. This test for determining if it's conservative says that it is. So f is the gradient of some potential function, some scalar field. And phi, we calculate that by integrating, and we get xy squared.
Professor,
Yeah,
the partial derivative of 2xy, is it not 2x?
the partial derivative,
2xy, is it not going to be 2x?
right? So my function g is 2xy. If I take the partial with respect to x, I get 2y.
Mhm.
I'm not sure. What are you asking?
Yeah, the second one, the y square is okay because it's 2y. My question is
Oh,
2x.
no, I'm differentiating this with respect to y. I'm differentiating this with respect to x.
So it still gets 2xy.
So this is 2xy. When I differentiate with respect to x, I get 2y.
Oh, okay, okay, I got
When I
it.
differentiate this with respect to y,
Yeah.
I get 2y, and they're equal.
Because I'm looking at the one at the bottom where you put down 2xy again, so that's why I'm confused. Where you have the 2xy down.
Oh, well, here, so
So you bring the question
So
back.
the partial, so I'm looking for a function phi which satisfies these two properties.
Oh, okay.
Partial phi, I'm looking for an unknown function where the partial phi with respect to x is y squared,
Okay, I got it
and the
now.
partial phi with respect to y is 2xy,
Yeah.
and the function y squared x or xy squared satisfies both of these conditions.
Okay, so that I got it now because I don't know that you bring the question back down. Thank you.
Yeah.
I got it.
Sure.
Question number 8.
Same set?
Yes. Linear integral.
Okay. So. This is page 1182, number 8, which is to integrate around a certain curve C, x squared minus 2xy plus y squared ds, where C is the upper half of the circle given by R of t is 5 cosine t, 5 sine t for t between 0 and pi. So that's the circle. When t is 0, you're here at the point 5, 0, and you're going counterclockwise around the circle from 5, 0 to minus 5, 0. So along this curve, x of t is 5 cosine t, and y of t is 5 sine t. Okay. And again, that means before I was calculating a line integral of a vector field, and now I'm calculating the line integral of a scalar field. So the definition of the line integral of a scalar field, little f, your curve goes from A to B. You take f of x of t, y of t, times the absolute value of this r prime of t vector dt. So here's r of t. What is the derivative of this, the tangent vector? The derivative of 5 cosine t is minus 5 sine t. The derivative of 5 sine t is 5 cosine t. The length of this vector is the square root of the sum of the squares of the coordinates. It's the square root of 5 squared sine squared t plus 5 squared cosine squared t. That's 5 squared, or 25, times sine squared plus cosine squared. That's the square root of 25, or just 5. So this magnitude of the tangent vector is just 5. And t goes from 0 to pi. So this is 5, the integral from 0 to pi, x squared minus 2x squared plus y squared. I guess one thing is you can just do it, right? This is x squared is 25 cosine squared t minus 2xy, 5 times 5, 25, times cosine t sine t, plus y squared, which is 25 sine squared t dt. Of course, here we have 25 times cosine squared plus sine squared, which is just 1, minus 25 times 2 cosine t sine t, which is the sine of 2t, for example, dt. If I take this 25 outside, this is 125 times the integral from 0 to pi of 1 minus sine 2t dt. That's 125 times what? The integral of 1 is t. The integral of sine 2t is plus a half cosine 2t. Because if you differentiate this, you get minus 2, which cancels the half, sine 2t, from 0 to pi. So this is 125 pi minus 0, pi, plus a half cosine of 2 pi, which is 1 minus cosine of 0 times 0. So we get just 125 pi as the answer. So, except maybe for some constants, if I did some arithmetic wrong, that's the answer.
Yeah. Professor,
Yeah,
number 3.
number 3. You're the only person with questions.
Yeah. Nobody is listening, so that's okay.
Okay, number 3.
Yeah.
Gradient fields. All right, let's take a look.
I guess
So
not.
this is page 1182, number 3.
Mhm.
Professor,
Yeah,
can you go back? I just want to take a picture. I'm sorry.
okay.
Really quick.
Yeah,
Okay, thank you.
okay, I mean, the video is also on, will be on YouTube, of course. Okay, page 1182, number 3. Let's take a look and see what problem that is. Find the vector field for the following potential function. Sketch a few level curves of phi and a few vectors of f. So we have the potential function phi of xy equals x squared plus 4y squared. And I want to look at this for x in absolute value at most 5 and y in absolute value at most 5. So what is the gradient of phi? So this is phi. The gradient of phi is the partial of phi with respect to x, partial of phi with respect to y. Partial phi with respect to x is 2x. Partial phi with respect to y is 8y.
Hmm.
So this is my vector field. What are some level curves of phi and a few vectors along the level curves? So for example, suppose I take the level curve phi of xy equals 4. That means I'm looking for all points in the plane. Phi of xy is x squared plus 4y squared equals 4. Or if I divide by 4, x squared over 4 plus y squared equals 1. And x squared over 4 is the same as x squared over 2 squared plus y squared equals 1. Well, this is an ellipse. That's an ellipse where the major axis goes from -2 to 2. When y is 0, x squared is plus or minus 4, and the minor axis is 1. So this is the level curve, the ellipse. And f is 2x comma 8y. So for example, what is f at the point 2, 0. It's just 4, 0. So at the point 2, 0, that's my vector field. That's my vector. At the point 0, 1, when x is 0 and y is 1, this is 0, 8. So here, the vector is pointing up. What about, see, what is this point? When x is equal to 1, y, so on this curve, when x is 1, you get 1 plus 4y squared equals 4. So 4y squared equals 3. So y squared is 3/4. So y is plus or minus a half times the square root of 3, which is square root of 3 is about 1.7. So this is approximately 0.85. Right, so that's this point. And f at the point x equal 1, y equal to root 3 over 2. What is that? So f is 2 times x, that's 2, and 8 times y, 4 root 3, which is approximately 2, and root 3 is about 1.7, about 6.8. So it's the vector which is going up sort of like this. Anyway, that's just an example. This is what they're asking you to do. Just draw a level curve. Every level curve is going to be an ellipse. And just pick some points on the ellipse and draw the value of the vector field there. And you get some pictures that look like this. Okay. That it?
The rest of,
All right.
I have one more.
One more, last one.
Yeah, you got it for me.
But I am, I'm back at 1 o'clock today and Wednesday, and again on Friday morning. But so
Yeah, I come back.
okay.
Exercise chapter 16, page 1084.
Chapter
16,
15
16:16.
and I'm sorry. So chapter 15, functions of several variables. What's the problem?
Chapter 16:16.
Oh, chapter 16. I'm sorry.
Yeah, page 1084, number 2.
Okay, just 1 second. Let me look for chapter 16. Chapter 16. Review exercises. And which number?
Page number 2.
Number 2.
Yeah.
Okay,
Thank you.
so page 1084,
Mhm.
number 2.
Yes,
So we have a double integral from 1 to 2
I want to follow.
with respect to y. And the inside integral is with respect to x going from 1 to 4 of xy over x squared plus y squared squared. So let me do the inside integral first. The inside integral is the integral from 1 to 4.
Mhm.
I just want to double check that I wrote it down correctly. 1 to 2, 1 to 4, xy, x squared plus y squared squared. Okay.
Yes, correct.
So this inside integral, I'm integrating with respect to x. So I could take this y outside. That's just a constant. It's x over x squared plus y squared squared. Okay? So I need to do this integral. So that's calculus 1 and 2. Let's say I make a change of variable. Suppose I let u equal x squared plus y squared. So du dx is 2x. So the indefinite integral, the integral of x over x squared plus y squared dx. So I have the integral du dx is 2x. So du is 2x dx, or a half du is x dx. So here I have x dx, that's a half du, x squared plus y squared is over u squared. All right, so when I make my change of variables, this is what I get. All right. I'm letting u be x squared plus y squared. So du is 2 dx. Sorry, du is 2x dx. So x dx is a half du. This is 1/2 the integral of u to the minus 2 du. Integral of u to the minus 2 is minus u to the minus 1. So this is equal to minus 1 over 2u. And I'm integrating, x is going from 1 to 4. When x goes from 1 to 4, u is going from 1 plus y squared to 4 plus y squared. So this is minus 1 over 2u, from u going from 1 plus y squared to 4 plus y squared. So this is minus 1, I can 1 over half, 1 over u, so 1 over 4 plus y squared minus 1 over 1 plus y squared. That's what this is. So if I multiply it by y, this is y times this. I get minus a half y over 4 plus y squared minus y over 1 plus y squared. So this is my inside integral. So this becomes the integral from 1 to 2 of this. Let me just write this. I have a minus a half. I just put this the other way. Y over y squared plus 1 minus y over y squared plus 4 dy. So I have to do this integral. Again, I can make a change of variables. Let me write this as, just to do one of them. Again, the integral of y over y squared plus 1 dy, by that u be equal to y squared plus 1, then du is 2y dy. So this is a half du over u, or a half log u, or a half the log of y squared plus 1. And so, I mean, the rest of it is just, you're just doing calc 1 again. Right? But I mean, this is, you have to compute the inside integral and then the outside integral.
Okay. Thank you, Professor.
Okay. All right, again, I have office hours, and if you can't make one of the office hours, but you have questions, just email me and we'll set up a time that works for you.
Okay,
Okay,
thank you.
okay. Okay, I'll be well. See you on campus on Monday next week.
And
Professor,
Professor, what's it? Are we, what's it? We're gonna keep on doing the review on Wednesday, right? Or do we have no class on Wednesday?
No, today's the last day of class.
Oh, today's the last day of class?
Yeah, semester's over.
Oh, cause I wanted to go through a couple more of the problems
Why don't you, so I have a review session on Wednesday.
on Wednesday.
Yeah,
Okay.
you can ask me then.
What
What
time?
time?
I don't know,
Okay.
officially, the last day of class is either today or tomorrow.
Okay.
But we don't meet on this, we don't have, this is a Monday, Wednesday class. So this
Okay.
is the last class of the semester.
Okay. Thank you,
So
Professor.
on Wednesday, it's gonna be what time?
Sorry,
What time on Wednesday?
it's set up for 1 o'clock.
Okay, cool. Thank you.
All right, okay. All right, everyone, be
Professor,
well.
can you hear me?
Sorry?
Can you hear me?
I did not, I didn't hear the question.
No, I'm saying, can you hear me? I was trying to.
I can hear you, yes.
Wait, so the finals is on Monday at 11?
The final is a week from today, 11:30 to 1:30 on campus.
Okay, 11:30. Okay.
Right? I mean, that's the, I have nothing to do with that. That's the time that the college sets. 11:30
Do
to
you know the
1:30.
room? Is it the same room as the midterm?
Yes,
Ah.
okay. All right, see you then, everyone. Be well.
Wait, hold on. Professor,
Yeah,
I had a question about exam 3.
okay, go ahead. I mean, the my lab exam.
Yeah. I didn't know it was due on the 9th. Is there any way you could make it due today?
Oh, if I can, I have trouble figuring out that website, but I will get into it and I will change the due date.
Okay, thank you.
Okay,
But
but,
when would it be due if you were to change it?
oh, I'll make it next Monday.
The next, all right, thank you. Thank you so much.
Yeah, okay.
All right, have a good one.
Okay, thank you. You too. All right, bye all.